Only mode.
Welcome everybody to follow the webinar about parametric structures. And today we're gonna talk about uh, a bit less known feature in our FEM-Design software. And this feature has like many uses, and it's much like underutilized among our users. So that's why I wanted to have this webinar, like show possibilities, what it can do, and also like give you ideas how you use the actual module. So first few examples, you can find it in the start menu of FEM-Design, and it's here. It's called parametric structures. And what it can do, you can make structures which has a parameters, and if you change these values, it will modify the structure. For instance, here you can set the Berlin division and the truss division, and yeah, you can make another part of same building, and it's really fast to make finite element models with this type of method that you define those parameters. And the trick is here that those type of structures, they are really easy to make. So it's even for single project like here, you have different sizes of trusses. It's worthwhile to do one block, and it works equally well with the shell models. Like here we have an example of bridge deck or bridge model, and you can equally well put parameters in here and make a structure with this easy. If you do like same type of bridges often, then it's worth to do a parametric block. And of course, this is a live event. If you have anything, you have something to ask with in this webinar, you can type the questions, and I try to answer my best in the webinar, or if I don't have time, then after it. So please just type the questions, and I try to answer my best. But here's the other type of structure, so it can be like lattice mast or anything that has a repetition. And here's the content of today's presentation. So first we're gonna talk about the basics, and then make some simple models, and then go to the bit more complex topics like how do you use and how you use grids, and then some examples, and finally like how you can do parametric solids and also loads. Okay, let's go to the basics. We start here. So what is parametric model? First you have to understand like what it actually is before you can use it. So it's a free modeling helper. So it helps you to build your finite element model much faster, but and it's better to use in small repeating building blocks of structure. And it's also good that you understand that it cannot update the existing model. So it's only when you're drawing something new. It's like another method to define a structure. That is what it actually is. And it's not the API or any kind of programming language. So it means that we have an API, and that's a different thing. This is much simpler and much faster. It's like just you replace your own drawing with this tool. That is what it is. And if you understand that it will never do like your whole structure, then you are using it correctly. So if you try to do it so that it makes even smallest detail a finite element model, then you are not using it very efficiently. If you understand this one, this is really important. That it makes like biggest part of your structure, and rest you adjust yourself. And also it's good that you don't put the whole model in the one block. For instance, we have this lattice mast here. Maybe we put the lower part in different block and the top part here in the other block, and then it's more usable because you might want to use like different type of like a lattice here in the top and in the bottom, and also same applies to foundation. So you can have a foundation plate on soil, or then maybe you have a pile, so you can change the bottom part. So it's never a good idea to put everything in the same block. Even it's possible to put everything in here in same block, but then it's less usable when you do so. And careful where you define the origin point of your structure, because that will be the input point. So it's like in this lattice mast example, if I put one corner as an input point, then it's really easy to put the next part of the lattice mast on top of the bottom one. And if you define parameters in these models, it's define them so that they are useful. For instance, we want to probably input this length of one side in this mast, so it's a more useful then. And if you understand that these blocks are quite fast to make, so it's sometimes it's even like worthwhile to use them for single use case, like single project. And also loading, I will give you good examples of this one. So loads can be also, or just loads can be one parametric block. So the basics, first you set the parameters in the table. So parameter table define those parameters. Then you define base rays, which are like lines, but they only work for 2D planes. Then you define base planes, and they work for 3D structures. And then you define grid. Grid means that it's a repeating same pattern. Like I have this lattice milestone, you have like concrete elements which keeps repeating. So that is a grid. Or like a truss is a good example of grid. And lock will lock like a physical part to those like base rays or base planes. And constraint will move those planes or rays. But we will look later how they work in practice. When we define like distances, you can see that there's a 2 base rays in the model, actually 4. And if you define these distances, you can define distances, 2 distances, and I can modify the both. But if I try to make a constraint now, let's try to put the constraint. And I try to put the constraint between like this base ray and this base ray, and I get this warning that they are not parallel. So that is good to understand. And if you want to define the distance, they always have to be like parallel to each other, planes or lines. That is like one basic principle of those. But that's basically all the concepts you need to build these blocks. Actually, I skipped one question in the beginning. Is the webinar recorded? Yes, it is, and we will publish this in YouTube later. So, but let's make the first block. So it's a 2D section. So we go to the parametric structures, and then we define region. Region is like nothing in finite element sense. Region is like a two-dimensional plane, so it doesn't have any strength properties. And region, what we are using when we are defining sections. And with the F12, we can feed in coordinates in FEM-Design, so we can type the coordinates in meters here. So we input one leg of the 2D shape, and then we probably, if we want to continue, maybe we can use our modify region command. So regions can be anything. They can be concrete shape, steel shape, or timber shape. So they are just like 2D shapes. And we can add stuff to the regions or take away something from the regions. Like here is the examples how you can modify those. But let's make the angles. So next part would be to make the fillets, and maybe and you can see that we can move corner points as well. So let's add a fillet here, because it's an angle bar, and probably they have fillet here, so we might have a fillet here. And you don't have to draw this shape in the correct size, because we put parameters later to like to modify the section, and we put like 1 centimeter fillet here. Okay, that is the shape. Then we define the base rays, because this is a 2D shape, so we only thing we need is base rays. Base planes are more for 3D, so we start here. And this is the base ray button here in the top left-hand side corner. So first base ray here, and you can see they don't have to be exactly where they need to be. You just roughly place them where they need to be, and of course you can copy these base ray objects yourself. And every place you want to move something with the parameters, you have to place a base ray. So it means the starting of the fillets, end of the fillets, and the corner points of the section. And same applies to here in the height direction we need to put. And this applies to 3D blocks as well. So you have to place these like rays or planes on the intersections of points. And you can see now it's defined. Now we want to lock that 2D shape to the base rays. And now it's important that I only pick like 2 lines. So if I pick more than 2 lines, it does not work, because they don't define a point. And I first click here, lock, and right click on the corner point of the shape here, and then pick only 2 rays. If I now select 3, it does not work, but let's try it again. Right click here, and only 2 planes or 2 rays. And now it works. So it's important that you only pick like two rays to define the location of the point. And you can see we didn't have to be like exact when we draw the shape. We just have to roughly have the shape there, and then we can put it in the grid like this. Then we set parameters and constraints, and it's important that we put it in the right order. So we define master and slave. So master is the one which remains the stationary, and the slave will move. So we start here by defining the parameters in the table. So we have already defined those parameters. And then we define here, like, let's say the width of the profile is from here to here, like this. And right click first on the master and then the slave. Then we want to probably define the thickness of the section. So it's going to be from here to here. And also the other wall thickness is it's here. Okay, that's fine. Then we want to define the corner radius, like here. It's probably from here to here. And you also can define that which will move, because they can form like a dimension change. So it's important that you first pick like what is the ultimate master and what is like the hierarchy of the structure. So it's like, for instance, here is we go like one back to define the corner radius here. And now the section is almost done. So if we modify the parameters, we can see that the section moves. So let's say we want to change the width of the section. Let's go to the let's change it to 150 and click apply. And you can see that the shape now follows. So that is like our first parametric shape. And final thing what we want to set is the radius as a parameter. So how it works. And if you try to move this inner radius, you can see that what is the problem here. If I move the inner radius, let's change it to something else like 5 centimeters. And you can see that it's quite not work as we think it would work. So we have to put some more parameters or constraints here. And there's a new type of constraints, which is a radial constraint. And then we can use the inner radius to define this radius here. And now it works when we change the corner radius, because also the arc radius have to be changed same time as the endpoints of the radius. Now you can see it works. Okay, we went like really slow with this first shape because this was like the basics. The 3D shapes will follow the same logic. And same here, corner radius and also the other corner radius. And then we want to save it to use it in the software. So now it's ready. So it's important that you pick like right angle where you place your camera, because it's saved in the as a preview picture, and you can even hide some planes or what you don't want to see in the preview picture, and then you can save it. I want to probably like hide this property here. Okay, now it's should be like fine. Maybe we want to only see 1 times the out radius. Okay, then we go to the file, and then we click here, save for the input wizard, and give it some kind of name. And how we use those sections. We go to the FEM-Design, and there's an input wizard on the right-hand side, and you can place it, but this is not how they're supposed to be working. So you can place them in 3D canvas, but now they are not sections. So that is like first way you can input them as a region and create plates. But let's use the plate beam command to really use them. We want to give them beam as a section. And we click here size, and there's a parameters, and then we can select the new I-beam with the flat or the new like double angle what we have defined. And now we can give it the parameters a value. And those which are calculated with the formulas now have been grayed out, so you cannot change those parameters. You can only change those which are like fixed value. Okay, and if this was too fast, I will send you, if you have registered to this webinar, I will send you all of these files to yourself. And you can see that it automatically recognizes that it's a compound shape. So it's made out of the flat bar and I-beam, and it automatically knows that it's a compound shape. So if you design it with the Eurocode, we know how it should be designed. And now we can make like real finite element beams with this section. So we can use it 2 ways. We can input them as a region to define anything, or then we can input them as new beams, like here. We can try this unequal angle as well. And again, we can change those variables like the distances and the thicknesses and so on. And they are always composite sections, so it means that they are like welded together, even there when there's a gap between those sections. And you can see now it automatically knows that it's a closely built up, made out of cold form sections. So it has like an automatic recognition of the profile for the beam design. And if we now look the results of the software, you can see that there's stresses. So we can do stress analysis of these complex sections, including the warping effects or 7 degrees of freedom effect. So any shape will work also there. And now you can see they are composite sections. And same if you want to design those sections, if you go to the steel design part of the software and check those beams, even though they are like parametric, the automatic shape recognition make it possible that you can design these with the Eurocode, even though you have made them yourself, like just with the collection of lines, they still work in the steel design. And here's the example of another section. This is a concrete one, and this is a concrete section. So it can be like really complex shape, and it really speed up the process of defining your structure. Any questions so far? So this is probably how you can use this section. So if you want to do something like this, you can use this section. If you don't have any questions, we can go to the more complex. There's a question: is it possible to do code check even double L section with the gap? Yes, it's possible, but you have to understand that it treats this double L section as they are welded together. So if you calculate the bending stiffness in cross direction, there will be like a really lot of weld between those two L sections, so there's a shear interaction between those. But if you take that into account in the designs, you put some flat bars to connect them, then it's fine. Then you can do design like buckling check and lateral torsional buckling check and warping and everything. And here's another example how you can use it in concrete design. If you are using a hollow course, it's really fast to now do different sizes of hollow course if you do it with the parameters. Let's do our first 3D model. So now we have to do it with 3D. And first we draw it. This is a pile cap. So it's a pile cap on steel piles. And first it's important that you move it close to origin. So if you want to input it, and probably like the column endpoint is the right input point. So it's better to move it like this. And then we have to define base planes instead of base rays. So base planes are those points where we want to define coordinates. So now we have horizontal planes. And with the FEM-Design coordinate system tool, we can also draw those vertical planes. So this we have to define one plane in the mid of the structure, and also in the pile endpoints and in the corners. And same applies to y direction. So we have to also define there some planes. So first the plane in the middle of the structure, and then we can copy it. And there's actually a faster way to do it, but this is if you want to manually do it, this is way to do it. So you have to put plane in every element intersection. And now we have to lock them in 3D, and still it's good you know how to do this manually. So 3D models requires 3 planes, no more or no less. So it means that if you select like 4 planes, it does not work. So if we select those 3D planes in 3D, we have to pick one corner point and exactly 3 planes. So if we take like this as an example, if we want to lock this into the grid, so we want to lock this corner point to the grid, we are shooting a 3D picking ray in the space. And if you think that if you shoot like ray through there, we right click on the point, and then we paint from the right to left over those planes. What happens? We hit, of course, this plane, we hit this plane, and we hit this plane. But the problem is that we also hit this plane number 4, and now it does not work. So we have to hide the plane number 4 to make it work. So there's a question. So every custom section should be parametric because when we make a section, let me see the full question. because when we do section in the section editor, it won't do design check. Actually, the new version of FEM-Design will allow design of any sections, even if you draw it yourself. But if it's something like really crazy that the automatic shape recognition doesn't work, then it works. But if you draw like angle, then it can do it perfectly. Or if you draw I-beam in the section editor yourself, then it works, even if you draw it yourself. So it doesn't have to be parametric to make it work. You can also draw it yourself in the section editor and still it works. Okay. So let's look how it works in practice. So we go to the 3D structure, and now we want to lock something in the grid. So we click on the lock here, and right-click on the corner point, and click here. And now the lock symbol appeared. So now it just hit in the 3-plane. So let's try it here. And you can see it just says bling, it does not work. So because you are shooting the picking ray and you are hitting like really many planes in the structure. So, and same here, we cannot lock this corner. So we have to do something here. So usually what I like to do is hide those unnecessary planes, because we only need like 3 planes to do the locking. So let's like show this plane. And then we need, of course, this plane and probably the horizontal plane. Now we only have like 3 planes. Now we can do the locking. So right click here and paint from right to left. And now you can see that the lock works. And if you want to do a second point, we have to show one more plane like this plane. And again, now it's really easy to lock the this piling plate corner to the grid. And now it works. Okay, now it's actually clear. What happens if there's more than one object in the single point? Like let's say that we want to lock this pile endpoint. There's a spring, there's a support spring to the bedrock, and also like the pile lateral spring endpoint. So you can see that there's really many objects in there. So there's 2 ways to do this one. So the first one is really easy, that you just hide unnecessary objects. So let's say we want to lock the spring, or do we want to lock the pile? So what we want to do, or actually this is also pretty nice if you move something, like move the plane or move the object. Like let's move this plane a bit off from the location. Now it's really clear. If you click here and then block here, you can see that it moves those objects like one by one. So now it's really easy to select those. So I can move everything one by one. And the second method is that I just hide those elements I don't want to move. Okay. And this is the second method. If you have like three separate objects in the point I want to lock, I can just hide, like let's hide this support and also the spring value. And now it's only thing what is left in the element crossing is the pile endpoint. And then I can lock that one. Now it's easy to lock in the. And how you use this, you just give those parameters value. So let's look like we want to use this one. So we give like this building some dimensions. I will, by the way, show later how you can use this piece, how you can make this building model. So let's say that then what is the like frame spacing? Okay, now I'm happy with the structure. I place it in somewhere in the 3D and some orientation. And there it is, and then we might want to use our piling cap model, what we just made, like this one. And then we can give it some parameters. By the way, if you use those lateral springs, they have to be divided in the height direction, because the soil properties and the capacity in lateral direction is the function of the depth and the density of the piles and many things. So now this is like too simplistic model, but it gives you idea how it works. So you can also include soil layers in your piling model. But you can see that how many things you can define just with one click if you are making like the whole piling plates, just like one block. And now you can copy or place it in many places. And the model is almost ready because it includes the calculation data. It includes capacities, support stiffnesses, and so on. So if you look like the model, it works just put the blocks there, and the blocks will include all the hinges and the connections and pile capacities and uplift. You can see that there's an uplift happening here, uplift the bedrock. So it's almost like ready to calculate when you are using those blocks. Of course, if you want to use, we have an automation, and that can help you. But of course, you have to first understand how this process works. if you do it manually, like I explained before, that how you lock those elements in those base ray and base plane intersections, and how you set constraints. But of course, you can speed up. So let's open one model like this bridge model to the parametric structures, and let's put some parameters here. And we don't want to do them manually, so that's why we have this automatic parameterization. So we just paint over the whole structure. It will automatically place those base rays and base locks and constraints. And if you don't like, okay, let's say this is a span, that's okay. This is probably not okay, so we just remove few constraints and define them again. So we can really speed up if we do use the automation. So first just draw the whole model and use the automation to place those locks and base planes on automatically. And then we can redefine. Let's say that we want to define like the width. Again, let's say this is a 15 meters, and what else we want to do. Okay, here is the x, what was the parameter called? It was x7, this one. We can call it span. And this is the cantilever part. So all those constraints what have been defined correctly, we can already like modify ourselves, and then put some new constraints in the model. So the automation can help you like to put those locks and planes automatically. So you just draw it and try it with the automation and fix rest yourself. So that is like really good way. And now we just define what the automation cannot define correctly. Let's say I want to define the width, what is from here to here, like the total width of the bridge deck, and let's say that we want to define something else like this chamfer part. We can define it manually. So it's automation doesn't know how you place these constraints. So that's why it's sometimes better to define these constraints yourself, like the transfer slab length. Let's say that this is 6 meters, and we want to define it from this wall. So from this wall to this wall, and now it's what we want. Actually, we select the wrong parameter. This is the transfer slab length. And now it's correct. So you can start with the automation and define these constraints yourself, like they're supposed to be. There's a question, how can we get the examples you're working on? I can send them. Everybody who has signed up for the webinar will get all of these examples automatically after the webinar. Probably tomorrow you will get everything. So you can try it yourself. And like the height of the bridge, you can define like this. So now this 3D block is ready. So if you modify something, you can see that if I modify like the transfer slab, now it works how I want it. And like the span length, if I modify or the cantilever part of the bridge, or the chamfer or anything, I want to modify this. So now it's very logical. So now I can really quickly make like one bridge model with all the supports and and it all can even include loads, like basic loading. And it didn't take long to make this because I used the automation to define those parameters. And final thing, what is like really hard to find yourself is what we have angles in the structure, like how to set those ones. So when one wall is in angle with each other, like here is like the transfer slab, but we can do it like this, that we have this drop of the plate, and this is the length of the transfer slab. So if you want to have it in certain angle, let's say that we want that slab is always like 10 degrees of like rotation, and also the local support is in that coordinate system. We can calculate the transfer drop with this fixed number. So it's easy. It's a sine function of 10 degrees, and that's the number. So you put the angle as a fixed number. And now if we change the height, length of the slab, it will be always in the same angle, like this. It can be anything, and it always remains in 10 degrees angle to the horizontal plane. Okay. The second example is this one. If you want to modify the angle, probably this is the easiest way to do it. And it's you can set like the x and y coordinates separately, and then it will rotate those elements what you want to be rotated. So it's easy to draw it that, then start the automation and then do it like this that you. And of course, it's not exactly the angle, but of course, then you can import it in the structure and modify it yourself. It doesn't have to be perfect. The most important thing here is that you make like biggest part of the structure with the automation, and rest you can do yourself. Any questions so far? Okay, we can continue. What about the grid, the repetition of parts? Let's see how that works. The grid basics is this. First you draw the grid and then you set some elements to the grid structure. So it has a properties. It has a division number like x. So it means how many grid cells there's in x direction, how many in y, and how many in z direction. And you can see that it has like 2 beams per grid cell, so that pattern keeps repeating on every cell, and that's why it's a 4. And then there's this checkbox that do you fill the end part or start part of the grid? And then there's also this property of and or, like the Boolean operation. So it means that if all of those, or even single one, like the y is blank, it means that the last part is blank. It doesn't fill that one. If it's a or, it means that any of them then can be checked, and then the last part will be filled. Okay. So how it works? First we define a grid like this. So this is the x division. This is the y or y distance, and then we click put mouse here and press F12 and set the z coordinate like this. And only thing now remains is to put elements into the grid. And here we can set the division, let's say like 3, 3, and 3, or whatever you want to put the elevation. And it's important when you draw elements to the grid, you only draw them once. So let's draw something like here. We draw a beam, or we can draw a wall or concrete element or whatever. So we draw it like from here to here and here to here. And maybe, okay, that's enough. Now there's elements. If you want that these keeps repeating in the grid, we can go to the properties of the grid, and there's a plus and minus. Plus means that it adds to the grid, so we add this one. And now they belong to the grid. It's important that you draw them just once, and now we can modify the division here. So we can modify the and also set these properties. Do they fill the last cell or not? Now the last cell is not filled. You can see that only those first 3 are filled. Or 1. Now it's just 1 in height direction. And of course we can stretch, we can change the height of the grid with the constraints, or just like manually modifying it like this. And it's important to understand that grid can be skewed. So it means that we can do something like this, or we can even change the height of the one end only. So let's say that I want to move this like up 3 meters. So the grid can also look like this. And it also can form a convex surface if we just move one corner like this. So they can be like really complex patterns. And if you don't want to have something that is not repeated, then it's important that you draw them separately from grid. So these upper and lower chords are not part of the grid. They are like just single members. They do not belong to grid because they are not repeated in the grid cells. There's a question: can we parametric the pile? Like we can increase the number of pile. Yeah, you can make a grid out of those piles. So if you want to put the pile cap example, that you can put like number of piles as a parameter. Yeah, you can have like spacing x and spacing y, and then it automatically places those in the edges or also in the mid parts, however you want. Yeah, it's a grid what you can use to do that. Okay, let's look at a more practical example. This space truss example, how we can do that one. And that is actually really easy to do. It looks complex, but it's not complex structure to do. So first we draw like non-repeating parts like that, upper chord and lower chord and start of the grid and end of the truss. And then we draw grid, and then we add some elements to the grid, so we can start it like this, that we draw beams like this. And this is funny because actually, if you draw this space truss here, it's actually faster to draw here than the normal FEM design, because it automatically copies these elements to the grid. So it's actually really fast to draw this type of structures with the grid system. And then you can just move this grid to the where the real truss lies. Like, let's put it here. So it was not that slow to do. It was actually quite fast to do it like this. And then we can change the division, like the division X. If we want to change it, it should change the number of elements in the truss like this. Then this is also something you probably cannot figure it out yourself. So you can actually overlap two grids with each other if you have a different patterns repeating or different repetition frequency of elements. So let's see an example here. Let's first try to like draw it like this, but it's probably this is not what we want. If we now want to apply this top part in the grid, it does not work, at least how we want it. We can click here, and that is not what we want. We don't want it in the bottom, and we don't want this pattern in the truss. So this is not the right way to do it. So we want to remove it from the grid. Okay. Better way, we do a second grid here, and you can see that it has a different division, because now we want to have a different division in the top part of the truss. So we want to have a different pattern and different like division here. So we need a second grid. And if you look the second grid, it has like the division is half of the first one. And of course, we don't have to have the repetition in the bottom, so we can take it away. So only the start part is filled like this. And you probably guess what is the next step. The next step is then just to move it on top of the original structure, like there. And we move it like there. And now we are almost done. Only thing we need to do is put constraints in the model to lock it. And we have a new parameter with this called count. So number of elements can be parameter. And if you go open the parameters table, we can put like a division of truss or division X or number of elements or number of like cell elements. And let's say it's a 12. And the type is count. It's important that you put it as a count. And you can have many, like division of upper chord, and that is also a count. And that usually, if you want to modify the upper chord, we can type formula like the division or the original division multiplied by 0.5 is the division of upper chord. And now we open the grid object and go to the setting of that one, and we set that this is the upper chord division, and this is the lower chord division or the basic element like division. Like that. If I modify this one, now it works as we want it. So now it should be done. And now only thing left is locking of grids. Of course, you can lock them manually, those grid corners, or you can use automation, like in here. If you want to be really quick, we can use this flash symbol, which is a new feature of FEM-Design 25. So you just paint over the whole thing. And now you already have the span as a parameter and all the constraints. Now you just have to modify those constraints a bit, because this is a stupid way to define those. So I just delete those, and same applies to here. But you can always start with the automation, so you don't have to manually draw those planes and put those basic constraints. I just modify these automation, like this is called span. And so on. It's you probably know how to continue from here. And the end product is something like this, that you can use it any way you want. So you can change the span length, height of the truss or division, and the endpoint distance and so on. And now you can just place it as I already visualized in the beginning. So there you have it. Each of those trusses are unique, and you can also use our blocks what we have defined before. Like I will show you later, but you can also have like foundations as a block. So they are really quick to define those foundations when you make a parametric block out of those foundations. And this is another example how you can make those blocks, but you should keep them simple. So if you are doing like scaffolding, you think that this would be hard to do, but actually this is really simple, because only thing you need is like actually like 3 elements to make this structure. So let's draw it like this, and you only draw them once when you are using grids, and then you just put them in the grid. So I add them to the grid, existing grid, like there, this one, and then the diagonal is the last one, like there. And now it's ready. It didn't take long to make, and now you can make a automatic parametrization of the whole thing, and there you are. The block is ready. It didn't take long to do a scaffolding model. And if you would want to do the scaffolding roof, this is how you do it. You make a grid, make a division. There's a question: how are the member releases done? Is there any option? You can put any releases if you like how the beams are connected or how the wall elements are connected together. You can put them in the parametric structure, and they automatically repeat it in the grid. And here's the example how you can use it. So, and the idea is that you put also those releases, and like here I have put like the weights on the length of the scaffolding as a parameter, or they are already included as the other grid in the lower part of the scaffolding. So you don't have to put those weights on the supports or anything. The idea is that you put as many as possible in the grid. And if you now place this one here, you see that the loads, like the weight of the on the foot, is already included, and the supports are included, and the hinges are included, everything. And you can see that if you make it simple, you can really easily modify these existing blocks. So you don't have to like try to make this opening in your scaffolding model. It's just take the basic block and modify those parts which are not repeating yourself. Maybe you want to have a narrow tower in the top, so you can do it like this. So do not try to make it so that you have this tapered part in the top. It's easy to make basic block and just delete the unnecessary elements and make a like roof as an element. And same here, like the basic roof as an element. And this is the roof division, and this is the truss division, how many trusses we have. I will soon give you instructions how to do this, but it's actually very simple model to do. And truss division, like what is the distance between two trusses, and then we can just place it in the structure. And there's like 700 beams in this model, and it took like 2 minutes to make like really easily, just by drawing few elements in the parametric structures. And this is how the end model will look like. And it can have like the uplift of the foundations is included, the weight on the foundations is included, so everything is already there. So this is how you do this roof part. So it's just inclined like a grid in the mid part. This bottom part is can be grid if you want to have multiple trusses, and this is like fixed part in the middle. So this is actually really easy to do and you can even do like half of the truss yourself and just copy it in 3D model. It doesn't have to make a full truss as I did it. So you just do this one, and this is how you can do it. And this is the final example. And this is actually, if you now understand how you can overlap grid, this is super easy to do. So this is how it works. So you can put number of frames, number of purlins as a different division, and what is the span to truss height ratio in your model, like all the essential elements of your truss model. Let's go how this is done. So if you now open this model, let's first isolate the columns. You can see that the columns, it's a simple grid. So it's a grid what repeats those columns in here. So that is like a very simple model. Let's look those purlins. And purlins are also grid. So it's a really simple grid what just fills the Z plus side of the grid, like here. The filling is only on the Z plus side. And like if you look these like the members of the truss, they are also separate grids. So if you overlap like many grids, you can do really complex stuff. And this is the end product. So you just overlap many grids to do it. So define the half span and just copy it in the other side. And maybe you want to put this as a spacing as a parameter. But I will send you also this model if you want to reverse engineer it, how it's done. But if you understand the concept that it's just like overlapping grids, it's not that complex. And if you do something that is not rectangular, you can do it like this, that if you want to do this lattice tower, it's done like this, that you just place those repeating elements on your grid. So each single side of that lattice tower is a grid. So it works like this. And now it's ready. It's so fast to do. And then only thing we have to do, because it's a tapered, it's an arrow in the top, we just have to taper the top part of the tower like this. And that's basically how you do it. And the real structure, it's just like 3 grids. So you just calculate the corner points in the bottom and top with the sin and cosine components, and place 3 grids in this triangular pattern. And that's how you can do this lattice tower. So actually that is also much simple than it looks like. And this is the end result. So you can calculate the overturning where the soil capacity is exceeded and when the tower is uplifted, and you can design the rebars of the foundations and exact deformation of antenna with the soil uplift and flexing of foundations and soil. And there's instructions how you can do it. So just do 3 grids and move those grid corner points with the sin and cosine components. So you just calculate like 3 corner points on top and bottom. And somebody asked that, do those hinges belong to grid? And yes, they do. Here's an example if we want to calculate like element stability, like wall elements. So here are the connection property, like concrete connections, but also beam connections are included. So all of these data will be included in the grid or in the parametric models. And if we modify anything, you can see that we can change the height and length of the structure. And the basic idea is that you never do like openings or things that are constant in the parametric block, because they are so easy when you have inserted the block in 3D that you can do those parts which are not repeating, like the doors or windows or openings, so they can be added afterwards. So you just put the repeating part in the parametric module and then add those things which are not repeated. Draw them manually, because otherwise the block will be too complex to use it for anything practical. And you can see this is the end result. So it's a nonlinear calculation, and you can see that concrete has a different spring value on tensile side and compression side. So you get really realistic model really fast, and you can calculate the overturning of concrete element wall system really fast if you put it in the parametric block, and also those edge properties are copied. And the final thing I want to talk about, if you don't have any questions, if you have anything, you can put them there. But let's continue if you don't have any questions. So parametric solids mean that also volumetric objects can be put in the parametric block, like here. And solids are drawn with the solid command here. You can draw any kind of solids like 3D shapes, and you can also do Boolean operations. So if it's a really complex shape, you can do like really complex 3D shapes. Like modify solid, it's here. Here is the Boolean operations, like make a hole in the solid, divide it, and so on. Intersection of or subtract. And this is a pile cap. Let's say that I want to do the pile cap, so we can put parameters here like the thickness, side height, size, and so on. The only like what is different with the solids, when you are locking those to the base place and base raise, you have to be exact, so they have to touch exactly the right point. But otherwise, it's equally the same as all the others. So here are the base planes what I have used to move those solid corner points. And the use of solids, it's here. Like you click like isolated foundation, and then you select parametric shape, and or then you can use the parametric tool to just import them as a solids. So here are the examples. So if you want to use them as isolated foundation, you click here and then just select the change shape or change parameters. I just select this pile cap. But please remember that if you're using this as a pile cap, they always have these foundations have a spring value under them. So you have to put that as a really low number. Now you can put it here and make it really fast like pile cap shape. And it includes the supports. So if you want to add piles, of course you remove the surface support or put the low value in the bottom. And this is how you can use it. Then you later add piles, or then you can make a volumetric or 3D block to also include the piles in the model. And also like isolated foundations, if you have rectangular, even that one is worthwhile to do a parametric model of that one, because now it's really fast to draw those isolated foundations with the rectangular. So like this one, or we might have an eccentricity or not. Then you need another version without the eccentricity, but basic idea is that you set the orientation and then you place as many as you want in the analysis model. And you can even change the shape. And other uses of solids, you can do anything with them. If you click here, and like this, I have made this building, so you can change the parameters of the building, like the size. So if you have like really complex shapes buildings, but they keeps repeating, so you can make like a volumetric object out of those as like a framework to draw your finite element model. So I can change these, and this is just made the automatic parametrization of buildings, so I can place it in any orientation in 3D, like here. And what I can do, I can use this as a scaffolding to draw like beams, like beam models, like this. Or I can use it to draw like shell models, like in this case, I can use it to draw hollow cores. Or then I can use it to draw covers. So I can also cover is like a facade of building which doesn't have any stiffness. So I can define facades or covers with this volumetric block. And I can use it also in the loading phase if I want to define like the climatic panel of buildings, like facades or roofs in this case. Or maybe I want to define the actual loading, like here. I can define a loading, so I can just select these areas. So it's easy to define. It can be also loading patterns. So I don't even know how you can use this, but there's many uses. You just make general solid or region and use that to generate anything else. And the final thing is we can also use it to generate just loads. For instance, if we have this UK National Annex type vehicle here, SV80, or we have a forklift, how we can do these with the parametric. So let's say here is our structure. And now we have built the blocks which only include loads. So let's see, we have a heavy forklift. By the way, you have to draw something, like I have drawn like a region here to make it work. It doesn't accept only loads. So if you draw some dummy object there, then it works. So just like the size of the forklift, now it's really fast to place that load anywhere. Like here, I want to place my forklift. And the loads tab, you can see that the heavy forklift is there. It's really fast. And you can use it later. Or let's look type vehicle, like here, the UK type vehicle. And it has a variable, this critical span here, or critical spacing. And now it's easy to modify. It can be like 3, 9, or 5, or 1.1. So you can modify, and also axial spacing or whatever you have put in the parameter there, or width of the vehicle. And let's place it here. So it's really easy to know. And what you can do now, you can define moving load with this type vehicle. So you can go to the moving load and put it as a moving load on whole deck, or define a new vehicle with that property. And the third use case, what I can give you is a checkerboard loading. And this can be slow to draw, but if you copy those span lengths here, and you have done this like checkerboard loading, now it automatically places the checkerboard loading on your model. So it's really fast to define a checkerboard loading in any model which has like a constant span. So it has 3 cases. We have a checker 1, like these cells are loaded. And now it's the same principle. You do not make overcomplicate your blocks. Just make something and then delete unnecessary part of your block. And then we have a full live load like here. But you probably get the idea how it works. Okay, let's see. We have some new questions. The region below, doesn't it affect the load distribution? No, it does not. It just like a region doesn't have any finite element properties. It's just a region, unless you do something with it, make a shell model. But it's just like a geometric shape. So just you can put regions anywhere, and they don't affect the finite element model. So, any other questions? Okay, it was a bit longer than I expected. You asked more, but it's still like under 1 hour. But if you have any further questions, of course, if you have signed up for the webinar, I will send you all of these models, and of course, we can offer help. So it's of course, if you want to help and do not know how to do something, I can help you to make those blocks, or anyone here in StruSoft. But thank you all, and have a nice day, and let's hope that I see you soon.